Okay, so let's first start off with a quick recap. Of the partition function. And in this case, right now we're only talking about the canonical partition function. Which we write as big Q, and it's n v t, or Q of n v beta. Sometimes mathematically it's just a bit simpler to treat temperature as this beta unit, which is 1 over the Boltzmann constant times by the temperature. Now, of course, everything we're doing here is absolute temperature. So the capital Q, this is for a collection of particles. And the term particle is sort of just used as a catch-all. What we really mean is molecules, basically, but in theory, right, we could generalize this to be any sort of particle that we'd like. We don't have to 100% represent a molecule in exactly one-to-one fashion. We can model it as a simpler form, and that's why I kind of use this generic catch-all for a collection as particles. Sorry. Lowercase q, this is for single particle. Now remember, the partition function is essentially a function that classifies all of the possible configurations or states of the system. So in the case of an ideal monatomic gas, now the ideal portion of this is really important because that means we're neglecting any interparticle interactions, which means we can treat every single particle as completely independent from every other particle. So the partition function, what we've approximated it as just the number of different ways that you can have translational energy. Right? In this one, we've neglected nuclear processes, we've neglected electronic processes, right? And in reality, those are actually fairly high energy processes, so they're pretty okay to neglect. We noticed that the x, y, and z were independent energy modes, and they were symmetric, so we just had to solve one and then cube it, and then that took care of things perfectly. So in this case, qx cubed is a perfectly good representation. We borrowed from quantum mechanics to know how the particle in a box behaves. Now, back in the classical form of this was derived assuming that molecules were not quantum particles, but were rather classical particles. But in this sense, it makes sense just to jump into the quantum mechanics explanation. And cube it because we're doing that 3 times, once for the x, once for the y, once for the z. So now what we said here is that this term right here, we called that a prime, and we said it was much, much less than 1. And because we said it was a very, very small number, whereas in this L, x is some integer, 1, 2, ... Right, since that a value is so small, the spacings in between the individual energy levels or energy states is very, very, very small. So it's a waste of our time trying to actually add these things up individually. So instead, what we're going to say is, let's just approximate this as a continuous function. So we're integrating from 0 to infinity of the same function. Okay, that's right, yeah. Sorry, I was just double checking. Okay, so this is our single particle partition function. The next action was to scale it up, not for one particle, but for a collection of particles of an arbitrary number n. Oops, that's not there yet. So to go from a single particle to a collection of particles, if they are completely non-interacting, the position and the properties of one particle is completely independent from all the other particles, then that's where we get this q to the n power. Right? Whatever the state of particle 1 is independent of state of particle 2, independent of state of particle 3, and so on and so forth. And this term right down here we call the indistinguishability factor. Now, one thing I forgot to mention when we covered this before, this is assuming that the number of energy states is much, much greater than the number of particles. Which basically means that no two particles can be occupying essentially the same state, which is a fine assumption as well. Yes, question?
So I just have a question. So earlier when you were talking about this, you said we'll pick a number of, like, say 1 mole or 1,000 different particles.
Mm-hmm.
Do you lose accuracy if you were to say, well, I'm going to assume that I only have like 20 particles versus having 1,000 particles?
So which part about the? Say that one more time.
Oh, if you use a low number of particles for your partition function, would you lose accuracy?
Would you lose accuracy? No. For what we're working on right now, it will be exactly equivalent, because we are not relying on the n as an approximation. However, when we go back to StatMech after the exam, there are some functions where we're basically, as a small side note over here, if we have to approximate n factorial, we can approximate with a function called Stirling's approximation. I don't have it written out right now. I think it's, where is Stirling's approximation? I have it here written. Yeah, it's, I just want to make sure I don't screw it up. Where is it? So in some of these instances, we do rely, here it is. So the ln of n factorial is approximately equal to n ln n minus n. So in some instances, we will rely on a large number of particles to simplify the math, in which case, yes, you may have some inaccuracies if you're doing this with a smaller number of particles, but it doesn't necessarily affect all properties in all calculations. It's a good question. Okay, so we have the partition function for a collection of particles, and we can calculate U as the average energy. Which we write as probability of being in state I with some energy multiplied by that energy. And then this portion of the equation there, that is the P of I. So recall that the partition function is the summation over all of the energy states weighted by a Boltzmann factor by its energy. Right, so the Q partition function is equal to It's a weighted summation. But this approach, of course, is for the canonical partition function, the NVT system. And then by inspection, when we look at the, the functional form of the partition function and how we come up with the weighted average energy, it turns out that the internal energy, U, is just equal to minus d ln q beta. Or we can write it out in this form too. This is at n, v being constant. So what we found was that the internal energy for a monatomic ideal gas turned out to be 3 halves n kBt, or 3 halves n over beta.
Well, you get it was 3 over 2r.
So in this case, if n is equal to, let me erase all that. I'm messing that up big time. Yeah, so if n is equal to na, therefore u is equal to 3 halves RT. This, of course, is because KB times by NA is equal to R. The Boltzmann constant times the Avogadro's number is equal to the gas constant. So what the gas constant and Boltzmann constant communicate is exactly the same information. The only thing difference is, do you communicate it for one single molecule or for a collection of 1 mole's worth of molecules? Right? The Boltzmann constant is the proportionality relationship between the velocity of a particle and its kinetic energy. So the gas constant then is the same thing, but as for a collection of particles. Okay, so that was our quick recap. So now we are going to look at your handout. First, we're going to describe the system. Then we have, let's see, I think there's A, B, C, D, E, 5 parts to this question. So we have a system of n indistinguishable particles that can occupy equally spaced energy levels. So we have energy level Z, E, 2E, all the way up to some arbitrary number of, J times E. This is in the canonical ensemble, so you can use the canonical partition function and all the math that we've talked about so far. Okay, so for parts A through C, the particle can only be in the first 3 energy levels. So that's what that drawing right here is. There's only 1, 2, 3 different energy states. Ground state with no energy, energy level 1e, or epsilon, energy level 2 epsilon. So, first question, write out the single particle partition function. So take a moment and write it out. And the amount of space provided on the handout should be roughly proportional to how much math or work is involved in the process. So in other words, it's not that much. So don't overthink it too much. So I'll give everyone a hint. So Q is what we're solving for here, right? The single particle partition function is equal to the summation over all the possible states scaled by the Boltzmann factor. Right, so how many different states can we have? 3. So you should have 3 entries into your partition function. Who feels good about their partition function? Only a few. So who wants to be brave and sort of commit to maybe where you guys having confusion maybe? I know there's some brave people. Okay, so we'll write it out real quick. So we're adding up our 3 energy states. We're scaling it by the Boltzmann factor. So what is the first energy state? E to the minus beta has energy of what? 0. Second energy state has energy epsilon. Third energy state has energy 2 epsilon. And so then the approximation, of course, this is equal to 1. That is the single particle partition function for this particular system. Yeah, question?
Is it still cubed though? Because it has translational measured like LX.
So in this particular one, it's not that complex. It's some special magical system. This could maybe be a model for the electronic energy states of a molecule absorbed on a surface or something like that. It doesn't have to specifically be sort of a fluid molecule moving around through the system. And so in fact, there's a really famous model that a lot of stat math classes teach, and we may get to it this semester, called the Ising model. So it's a 2D grid of spins, either an upspin or a downspin. And so that's a very famous model that has lots of applications outside. I mean, it's used very heavily in, let's say, like magnetism, for example. But it's the Ising model. A lot of problems can be converted down to a 2-state model. Is it an upspin or a downspin? So this is just a very simplified, not particularly appropriate to a real fluid, but a system that very well may be taught to understand the basics of partition functions. Okay. Any questions? The tricky thing with the partition function is that it's a summation of all the different states, but then somehow you end up getting this continuous function that spits out, and then somehow you take the derivative of it and it just gives you a very reasonable number. So it works out. It's not super magic, but it's a little bit abstract for the start. So let's go to the next question then. So, what is the degeneracy of the 3 epsilon energy level, right, not energy state, for a collection of 3 particles? Right, so what we're asking for is this capital omega of 3 epsilon. So if we were to rephrase this, what I'm asking for is what is the number of ways that you can organize 3 particles that are indistinguishable into a number of energy states such that the total energy level of the collection of those three particles comes out as 3 epsilon. Right? So we're going to do this one twice. Once for indistinguishable particles, and then once for distinguishable particles. So I just wrote down how I set mine up. On the indistinguishable particles, you don't care which particle's which, so I organized it based on energy levels. But for the distinguishable, I started building a little table so I could keep track of particles 1, 2, and 3. Okay, what about the indistinguishable? How many possible ways can we have an energy level of 3 epsilon with indistinguishable particles? Got to vote for 6. I got to vote for 2, 3, 2. I got 2. We can have, let's see. How do I write this? Actually, you know what? Well, I did shorthand notation. I'm not sure this is the most convenient way. So how I did it is if we had these 3 energy levels, we could have all 3 of them with an energy of 1 epsilon, or we could have, let's see, 1 with 0, 1 with 1, and 1 with 2. I think those are the only 2 ways that we can get a total energy of 3 epsilon. Yes?
Why can't we have 1 and 3 epsilon and 2 and 0? I know you didn't draw 3 epsilon on there. Is there a reason we can't use the 3 epsilon energy level?
So in general, yes, we could. For this particular one, I guess I didn't make explicitly clear, for parts A and A through C, it's only the first 3 energy levels. But in general, yes, that's totally fine. But for this one, I wanted to make it simplified. So for this particular one, it's only the first 3 energy levels. So 1 and 2 different ways. Right? The particles are indistinguishable, so it doesn't matter which one goes into which bin. So let's just quickly go through the distinguishable one. Did anyone get an answer for distinguishable?
6.
I got 7 as well. So I got, let's see, 1, 1, and 1. So energy levels of maybe I should write this as, let's see, let me do it differently. Epsilon, epsilon, epsilon. What else do we get? Just trying to swap them out. That should be 7 entries, right? 1, 2, 3, 4, 5, 6, 7. So in this case over here, 3 epsilon omega is equal to 2, and in this case here, the degeneracy of the 3 epsilon energy level is 7. Just keeping track of all of the different combinations. Any questions? Yeah. So, we would use the indistinguishability factor if we were sort of generalizing this potentially. So in the case of the ideal gas scenario, where we had basically the partition function for single particle 1, the partition function for 2, for 3, for 4, so on and so forth, right? We wrote this as q to the n power. Now this combinatorial approach is only valid if you have distinguishable particles. And so when we scaled it up to the q for indistinguishable particles, that's where we had to add in the indistinguishability factor. But for this particular example, it's written in a form that it's manageable to actually write down all of the possible different energy states for a single particle. So when we scale this up to a collection of particles, then yes, we would have to include the indistinguishability factor. For now, we're just keeping tally of a single particle partition function. Okay. Next part. Again, there should be a C. For the single particle system, again, we're only at energy levels 0, 1, and 2. What is the probability of a particle having energy epsilon at infinite temperature? So conceptually, you might be able to get this one right away. Mathematically, it takes a little bit more. So does anyone have the conceptual answer? What is the probability of being with energy epsilon at infinite temperature? But again, this is a simplified system, only 3 energy states. 1/3. Right? At infinite temperature, remember, everything is equally probable. So it's just as likely to have 0 energy as it is infinite energy at infinite temperature. We're a bit short on time, so I'm just going to go through this one really quickly. So the probability, in this case, it's the probability of being at energy epsilon minus beta epsilon divided by the partition function, which is 1 plus e to the minus beta epsilon plus 2 epsilon. So as beta goes to 0, as t goes to infinity. So in this case, it's e to the zeros all around, right? This is 1 divided by 1 plus 1 plus 1, which is equal to 1/3. Right, because having the infinite temperature in the beta basically means that this term doesn't matter. Who cares? It doesn't matter what your system is. It doesn't matter how high energy it goes. Infinite temperature is infinite temperature. So the goalpost of what we classify as infinite versus not infinite temperature, though, is going to be dependent on the particle system. Right? Can you assume it's at infinite temperature or not? Okay, now this is where things get a little bit trickier. So for the last 2 parts, the system is now unbound. But we're still dealing with just a single particle partition function. In this one, okay, so it's unconstrained, right? So the energy level can go to infinity. What I'm asking in this one is to derive the single particle partition function, which is given already there. So you already have the answer. It's just a matter of how do you actually go through the processes to get there. So since we're short on time, we can just go through this one as an example. So step 1 is we need to generalize. Right, our partition function only has 3 entries. We can't scale that up to an infinite number. Right? So what we need to do is generalize our single particle partition function. Can somebody think of a simple way to generalize it? Integral. Let's go one step back. Let's talk about the summation. Right? So I'm going to say Q is equal to the summation of e to the what?
Negative beta epsilon, or negative beta epsilon sub I.
Very, very close. I would say minus, we could say I or J. For some reason I put J in my notes here. Starting from J is equal to what? 0 to what? Infinity. So this captures our single particle partition function for the simplified system. Right? The first entry is e to the minus 0, right? The next one is 1 epsilon, the next one is 2 epsilon, and so on and so forth. And then we're going to approximate this. As stated here, we can approximate it as a continuous function. So we're going to go from 0 to infinity, e to the minus j beta epsilon dj. We're going to integrate our function. Beta and epsilon are constants, right? Of course, the beta is constant because we know we're in the canonical ensemble. NV beta. Epsilon is constant because it's dependent only on the system physics, basically, how we defined it. So that we can write this integral as minus 1 over beta epsilon times by exp of minus j beta epsilon from 0 to infinity. This is minus infinity, sorry. This goes to 0, this goes to 1, and we spit out our single particle partition function as 1 over beta epsilon, which is what we had up there. Procedurally, this should feel exactly the same as what we did for the ideal monatomic gas. The only thing that's different between this system and the ideal monatomic gas is we had a more accurate partition function, or a more accurate way to keep track of the energy levels of the ideal gas particle. But procedurally, nothing has changed at all. All we're doing is we're summing up all of the possible different energy states. The math is a bit more complicated when we're dealing with a real system as opposed to a simplified system, but so far, procedurally, everything is exactly the same. So the key differences between this model versus the ideal gas model is that, well, one is more accurate and actually has some real physics behind it. Okay, last question is using the single particle partition function that we derived in part D, what is the internal energy for a collection of indistinguishable particles at constant, NVT? So what is the internal energy for this particular system?
Definition, we start with the definition U is negative natural log Q divided by beta, right?
Yep. And that is on the equation sheet as well. So if you have the equation sheet, if you go all the way to the bottom, you'll see that there's a lot of the same stat mech functions. So Carlos, this goes back to your question exactly then. Now we have to have the indistinguishability factor involved in this one. All right, so we need to calculate Q, and that U is equal to minus D ln Q D beta. So strictly speaking, this is a plug and chug problem. Okay, normally I'd like to give you guys a little bit more time, but since we are short, I'm going to just work through it. So if we take what we have from the previous problem, the natural log of the partition function is going to be equal to our partition function that we came up with was 1 over beta epsilon, which is equal to beta epsilon to the minus 1 power. So from log properties, we're taking q to the n, and we have the minus 1. That's where we get the minus n here and minus n there. The beta and epsilon are multiplied together, and that's how we can separate them through the log properties. And then, of course, this factor right there is the same logic, but just for the indistinguishability factor. So when we calculate the minus natural log of the partition function with respect to beta, we get that this term goes away, this term goes away. And we have n times d beta of the natural log of beta, which is just equal to what? 1 over beta. So we get n over beta, which is equal to n kBt, which is our internal energy. So, what we've done so far is focused on the most complex system we've done is the ideal monatomic gas. So if you go into the end of chapter or end of book correlations for heat capacities, those are the ideal gas heat capacities for heptane or benzene or water or whatever the case is. And in those circumstances, basically, we can take the same approach that we've taken here, where we've broken down the individual energy modes that the gas particle can behave in. Right, in this case, the monatomic one, there's no rotation, there's no vibration. All that it is the translational energy. But if we take a complex molecule, like hexane, right, you have its translation, you have a number of different vibrational modes, you have a number of different rotational modes. The whole molecule can rotate, it can rotate internally. These are all of the different ways that the molecule can store energy. Every single one of those energy modes contributes to its heat capacity. So now it gives us sort of really a fundamental understanding of why different compounds have different heat capacities. So but then when you go to a water, or a liquid instead, you can no longer assume necessarily that you don't have any interactions and that your energy modes are completely independent. And that's where things start to get very, very complicated. And that's where basically it's easier just to perform a molecular simulation than it is to try and quantitatively write all this out algebraically. Okay, any questions? Okay, so we'll do a recap on Wednesday and then exam on Friday. I forgot to post the practice exam on Friday. It's up there now. So please check out the practice exam. And yeah, office hours tomorrow. Take care.